Humanity has long pondered the possibility of traversing the cosmos via space travel between stars. This has only been our imagination up until recently, but thanks to recent technological advancements over the past 50 years, this idea is now a real and exciting possibility. In addition, as our search for extraterrestrial life expands exponentially and as we learn more about Earth's limited resources and environmental issues, interstellar space travel is becoming increasingly important. According to Parry, it has been hypothesized that Earth could sustain life for an additional 1.75 billion years in the unlikely event of no major natural disasters. This figure is based on the fact that around that time, our Sun will have exhausted a significant amount of its hydrogen fuel through a process known as nuclear fusion, resulting in a decrease in its mass but an increasing release of energy as solar radiation. Earth will be removed from the Goldilocks zone of our solar system, which is the region where liquid water can stand at the surface of a planet based solely on its orbital characteristics, and will become increasingly too hot to support life as we know it after approximately 1.75 billion years. You might think that this is a long time for humans to leave Earth and settle in other solar systems, and you would be right. However, it also assumes that Earth will not become uninhabitable due to other factors like a large planetary impact or rapid climate change. One way or another, our experience on planet Earth is limited, making it unavoidable that in the close or far-off future, we should choose different planets and, surprisingly, other star frameworks in the smooth manner. Naturally, this necessitates transporting a large number of people across vast interstellar distances, assuming at the very least that we retain our present physical form, a task plagued by numerous issues. Although it is obvious that interstellar distances are vast, it can be challenging to comprehend just how vast they are. Proxima Centauri, the other star closest to us, is 2,667 times as far away as Pluto is from us. From Proxima Centauri, it takes 4.24 years for even light, the fastest object in the universe, to reach Earth. Sadly, the technologies currently used in spacecraft are simply unable to cover such vast distances in a reasonable amount of time, much less transport hundreds of people to other solar systems. It would take over 115,000 years to get to Proxima Centauri even with the fastest crewed spacecraft ever, traveling at approximately 40,000 kilometers per hour. To put this into perspective, the Homo sapiens species only developed speech as a cognitive function around 50,000 to 150,000 years ago. As a result, it would take the same amount of time for the generations of humans aboard the spacecraft to reach their destination as it would for the entirety of human verbal communicative history to unfold. The rate of adaptation and evolution of people on such a mission would dramatically decrease in the confines of a spacecraft, with little to no selective pressures other than perhaps the ability to cope in such an environment, and the ever-increasing amount of time required to send and receive transmissions with humans on Earth. It's possible that by the time such a crew reached Proxima Centauri, they would be as primitive as cavemen are to us right now if humanity on Earth didn't suffer any major catastrophes and continued to learn and develop new technologies. This is a troubling thought, but it demonstrates that if humanity is to leave Earth and explore other solar systems, new ideas and faster space travel are required. Chemical-based fuel, which is cumbersome to carry and extremely inefficient, has been the source of power for all rockets used up to this point. To generate thrust and accelerate the spacecraft, chemical fuels make use of the energy that is released as a result of the rearrangement of bonds that occurs during chemical reactions. However, these kinds of reactions only change the arrangement of electrons in atoms, which only make up 0.05% of the mass of hydrogen. According to Einstein's general relativity's mass-energy equivalence equation, when two masses interact, less energy is released because energy equal mc² holds. This can be used to figure out how efficient chemical fuel is, which is only 0.0001%. To cut interstellar missions' travel times down to a manageable length, we clearly need to develop more effective power sources that can propel spacecraft to much higher speeds than currently possible. Fortunately, a number of exciting new technologies are in development, and many more theoretical solutions may become feasible in the near future with increased scientific knowledge. Nuclear fusion fuel is one exciting new idea. Nuclear fusion is the process that occurs in the core of the Sun and other stars when extremely high temperatures and enormous gravitational pressure cause small atoms like hydrogen to fuse together to form helium and larger atoms releasing energy. This process has been recognized for some time. Spacecraft powered by nuclear fusion fuel attempt to replicate this process, but the temperatures necessary to start these reactions cannot be reached without the enormous pressures created by stars' centers due to their gravity. As a result, novel approaches are required to consistently heat hydrogen to the temperatures necessary for nuclear fusion reactions. The ITER magnetic confinement reactor, which is currently being developed in France, is one such approach. The nuclei of these massive electromagnetic superconductors can fuse into helium and generate energy thanks to the pressure exerted by a central ring of hydrogen gas in the plasma. However, in order to stabilize the system, a network of tubes containing liquid helium cooled to -270 degrees Celsius must surround the superconductors in order to prevent them from vaporizing themselves. Maintaining this requires a significant amount of energy, and the energy required to carry out the reaction currently exceeds that of nuclear fusion. Nuclear fusion, on the other hand, may be approved as a more powerful and efficient means of powering the next generation of spacecraft if this technology continues to be improved. Nuclear fusion reactions rearrange the proton and neutron nuclei of atoms, entities with significantly more mass than electrons, producing approximately 10,000 times more energy per unit mass of fuel than chemical-based fuel, which uses only 0.05% of the reagent's total mass. As a result, nuclear-based fuel-powered spacecraft could accelerate for much longer periods of time, and reach speeds that are significantly faster than those currently in use. Furthermore, hydrogen isotopes, the most abundant elements in the universe, are the only reagents required for hydrogen nuclear fusion. Future spacecraft that make use of this technology might be able to collect cosmic hydrogen as they travel, feed the hydrogen into the reactor, and keep producing thrust. As a result, the spacecraft's mass would be greatly reduced, allowing it to accelerate to higher speeds and reduce the initial hydrogen consumption. Laser-powered propulsion, which is well known for its use in the Breakthrough Starshot program, is another proposed method for significantly increasing the speed of spacecraft. Due to the fact that the energy comes from a ground-based source, this revolutionary technology eliminates the requirement for fuel on board. The spacecraft is able to accelerate to much faster speeds as a result of this significant weight reduction. In order to accelerate the spacecraft that is currently in orbit, a massive reflective light sail is attached to a ground-based array of high-power lasers. The total mass of the spacecraft and the combined energy output of the laser array must be in the hundreds of megawatts range for it to be effective. However, the Breakthrough Starshot program predicts that their 1-gram probes can be accelerated to approximately 20% of the speed of light, a remarkable achievement that would cut the travel time to Proxima Centauri to just 22 years. This would enable the mission to be completed and the data to be returned to Earth well within a human's lifetime, which would be more than 5,000 times faster than the fastest crewed spacecraft to date. Scaling up the technology to power a spacecraft that can carry passengers on its journey is an obvious engineering challenge that may not be possible. In addition, there is no current solution for how human passengers would withstand the force generated by traveling at such speeds. The construction of a light sail that is big enough to reflect enough energy to power a spacecraft that is many orders of magnitude heavier than the ones that are currently in development will be one challenge. However, the most difficult challenge will be getting the energy needed in the first place. There are theories for future energy harvesting techniques that may make it possible. These ideas, which are beyond the scope of this video, include making a Dyson sphere or extracting cosmic hydrogen for fuel cells. The spacecraft colliding with interstellar dust would completely destroy the light sail at such high speeds, which is another issue with laser beam propulsion. Breakthrough Starshot will try to avoid this by sending thousands of probes into Proxima Centauri with the hope that at least some of them will survive. To theoretically reach the unreachable universe, there are even speculative means that are permitted by our current laws of physics. These means could allow for travel at a speed faster than light. Wormholes and warp drives are two dominant and exciting theories. Wormholes are hypothetical phenomena that arise when two extremely dense objects, like two black holes, distort and bend the fabric of space-time to such an extent that a tunnel is formed between them. This could take place between 2 points in space or even in parallel universes. While Einstein's theory of general relativity allows for the existence of wormholes, there is no evidence of them at this time. Sadly, even if wormholes were discovered, it is also theorized that any matter, even a single particle, passing through the wormhole would set off a catastrophe and cause the wormhole to collapse. Antimatter could theoretically stabilize the effects of regular matter passing through by feeding antimatter into the wormhole, with whatever matter is trying to pass through. In a similar way, the idea of warp drives relies on our understanding of spacetime provided by general relativity. This is a hypothetical technology that would be attached to future spacecraft and would distort spacetime in front of the craft, drastically shortening the distance between it and its destination. Spacetime could be shortened in front of the spacecraft, and lengthened behind it by carefully and shrewdly exploiting large quantities of matter and antimatter. This would create a stable bubble of space around the spacecraft, and enable it to travel to a specific location much faster than the speed of light. Despite the fact that neither of these approaches to traveling faster than light is currently conceivable, the fact that they are both possible under our current physics laws is extremely exciting. These models might become real-world technologies, and enable humanity to freely explore the cosmos as a result of future discoveries and information about dark energy, dark matter, antimatter, and black holes.